Alright, so as we have seen in the previous clip, another way that initial conditions may matter is if a chain has a periodic structure. There are many ways of defining periodicity. Some of them are more mathematical than others. Let us consider on one of the most intuitive ways of doing that. So here is the definition. The states in a recurrent class are periodic if they can be lumped together or grouped into several subgroups so that all transitions from one group lead to the next group. So what does that really mean? Let us try to parse out this by looking at a given example. So here we would have a situation, a structure of a diagram, in which d is equals to 2. Whenever you are at a given time in a state in that group, in the next transition you will go to that group. And if you are in that group, at the next transition you will go to that group. So in some sense there is periodicity and there is somewhat of a deterministic behavior according to this transition, but there is also some randomness left. We can be in any of these states within that subgroup, but one thing that is for sure is that whenever at a given time you are into one of these states here in that group, if the Markov chain has this specific structure, in the next transition you will transition to one of these states here, and the next transition after you will go back here. So essentially, if your Markov chain started in one of these states here at time n equals 0, then at time n equals 1 it would be here, and then at time n equals 2 it would be here, times n into 3, and so on and so forth. So every time you would have an even number, then you are guaranteed that the Markov chain will be in one of these states here. Clearly, with this kind of structure, it is impossible to have convergence of the steady state probabilities. This is another example where you would have a structure of a diagram in which you have a period of 3 here. So in that case here d equals 3. So here again, if you are in one of these states at a given time, then at the next time the following transition will guarantee to bring you in that group, and during the next transition you will go to that group, and then again here, and again you will have this kind of behavior in a very systematic way. So if you started here at time n equals 0, you would be in that group here at times n equals 1, and you would be here at n equals 2, and again n equals 3 here, n equals 4, n equals 5, 6, 7, 8, and you see the pattern. If you look at any time in the future, if the time is of the form 3 times k, for any k greater than or equals to 0, you're guaranteed that your chain will be in one of these states. Otherwise, it will be here or here. So here again, you do not have convergence of the steady states, because if you are told that you started in one of these states here, then you know that whenever you have a time that is of the form 3k plus 1, you will be here, and so the probability of being here will be 0. Alright, so we have been able to explain a little bit what a periodic state is using this definition. Now, given a Markov chain, how can we tell whether a Markov chain is periodic or not? There are in fact systematic ways of doing it mathematically, but usually within the types of examples we see in this class, most of them, it will be easy to see, we just eyeball the chain and we tell whether it's periodic or not. So let us see if it is that easy to do and consider that chain here. Okay, so let's see. Is this chain periodic or not? I will give you a couple of seconds to think about it. Now I'm going to help a little bit. I'm going to just decide that this one will be red, this one will be red, this one will be red, and this one will be red. Now I'm asking the same question. What do you think? Well, from the structure, it is clear that this Markov chain is periodic and has a period of d equals 2. In some sense, the red state here could be one of these group. These are the red one. And the white here would be those here. And it is clear, if you look at this diagram, that whenever you are in a red state, at the next transition, you are guaranteed to be in a white state. From this one you will be in white, from this one you will be in white, from this one as well, and from this one as well. And whenever you are in a white state, this one, this one, this one, this one, or this one, at the next period, you're guaranteed to be in a red state. So this tells you that sometimes it's not that easy to eyeball and decide if a Markov chain is periodic or not. If you have, for example, lots of states, you might have some trouble doing this exercise. On the other hand, something very useful to know. Sometimes it's extremely easy to tell that the chain is not periodic, even if you have a lot of states. What is that case? Well, look at this case here and suppose for a moment that you have a self-transition here. Well, in that case, you would have a transition from a white state to a white state. And you're not guaranteed anymore that from a white state you would go to a red state. In that sense, as soon as you have a self-transition, the Markov chain is aperiodic. It cannot be periodic. So whenever you have a self-transition, this implies that the chain is not periodic, and usually that's the simplest and easiest way that we can tell most of the time that the chain is not periodic.